All right, ladies and gentlemen, this is our first of two videos on graphing sine and cosine. The first video is going to be the basics, and the second video will be the graphs or some examples of graphs. All right, so we're going to take this hopefully nice and easy, going through the graphs of just sine and cosine, and the next couple days we'll go over the other four functions. All right, so you see a lot of the key concepts that we're going to be dealing down here. I haven't really put this down here before, but there's a lot of things that go along with graphing sine and cosine and tangent and all the other three. Things like period, phase shift, vertical shift, domain, range, amplitude, graphing the parent function, and goes on forever. All right, and then ultimately, obviously, the goal is to be able to graph these two functions in any form, not just the parent function. All right, so let's go ahead and get going here. This word here, if you want to pronounce this out, this is sinusoid. And what a sinusoid is, it's a function that can be written in this form. A times the sine of bx plus c plus d. Now, the reason I'm putting A, B, C, and D in the color red is because they affect the graph in different ways. We are going to start with the parent function, just sine of x. That's what we're going to start with in a few minutes, but right now I'm just going to discuss the sinusoid a little bit. And A, B, C, and D are just constants, and A and B cannot be 0, but they can be any other number. They could be fractions, they could be decimals, they could be anything. They could be negative also. They just can't be 0, because if A was 0, then this whole thing is 0, and we're left with D, which is a horizontal line. Boring, not a trig graph. If B was 0, then we'd be doing sine of a number, and sine of a number is just a number, and again, it's just a horizontal equation. Now, as we'll see in a little while, the reason for this, but sine and cosine are both considered sinusoids because they're basically the same graph, only a cosine is kind of a translation. It's shifted left or right from sine. So let's start with the parent functions. The parent function, first of all, either sine of x or cosine of x. What we're going to do is use a table of values to graph the sine of x or the cosine of x. And I am going to do this on a computer program called Desmos.com. If you don't know about Desmos, I'll show you what it looks like here. Oops, have Desmos up here somewhere. There we go. So we're going to look at sine of x, and if you know Desmos, you can actually do this here if you would like. You get rid of that undefined. Oops. Add a table, just x and sine of x. All right, so what we're going to do here, you notice on my x-axis, what we want to do is we want to go from 0 to 2 pi, because that's like going around the circle all the way once. So if you're making your x and y axis, on your y-axis you want to go out to 2 pi, and you want to put in all of the quarters. So 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, and 8 quarters. Now on Desmos here, obviously I can go for as far as I want. And on the y-axis, you need to go up to 1 and down to -1. Now before you plot anything on your own graph, let's go ahead and look at what the table is going to be. So we're going to look at our special angles. So let's just start at 0. If I plug in x equals 0, I get a 0. Let's change the color here, something we can see. Let's go to red. Okay. So I get the 0.00. If let's just go, oh, why did I do that? Oops. There we go. Okay, so I still go from 0 to 2 pi. I go up to 1 and down to -1. Let's put in 2 pi. Let's go to 2 pi. Oops. And on Desmos, you can just go 2 pi. And if I plug in 2 pi, I get, 0 again. Okay. And we know this. If you're going through your circle, the y-coordinate here is 0. Let's go to pi. Oh, that's 0 again. So it's kind of looking like everything's 0, but we know it's not because of the y-coordinates on our circle. So let's look at some more interesting ones. Like, let's try our 90-degree angles. Let's go pi divided by 2. If I plug in pi over 2, I get 1. So I'm up here at +1. If I plug in 3 pi over 2, you should probably figure out that that's -1. So let's put in some intermediate ones. Let's put some stuff. Let's put in pi fourths. And let's try 3 pi fourths. I know this table is getting kind of long, but you don't have to put all of these. I'm trying to get a sense of what the shape of the graph is going to be. And I'm going to put in 5 pi fourths. And I'm going to put in 7 pi fourths. Now we have a couple more angles that we can put in. Let's do the 30-degree angles now. Let's go pi over 6. And you kind of follow along here. You look at what is this shape? What is this shape starting to look like? Obviously, it's looking like a sine graph, but what kind of else is going on here? So set 5 pi over 6. Let's go 7 pi over 6 and 11 pi over 6. And you start to see this curving effect going on. And if you were to start to draw the lines in, it kind of looks like it should go up here and come on down. Obviously, you're going to use a solid line for this. Oops, missed a dot. Oh well. And lo and behold, I can go back up and I can tell the, oh, it just got rid of my dashed lines. That's interesting. Let's try that again. Notice, though, I don't do any corners. This is a rounded curve. It's very, very smooth. Very, very smooth. And if I go back up and I just tell it to actually graph sine of x, which you can do, obviously. Look at there. It graphs the sine of x function. It follows all of these dots up and down. Now, what you'll notice here, watch as I zoom out on this function. And this is why Desmos is very, very handy. It's harder to do on a graphing calculator. But Desmos, if you were to zoom out, you start to see the same pattern over and over and over again. It's actually kind of nice how those little red dots are kind of creating that curve now, because we call this one full period of the function, because this little section in red gets repeated again here, then it gets repeated again here, and it gets repeated again here, and forever and ever. And the farther you zoom out, it just continues, and it will go forever. And since it goes forever, the domain is all real numbers. That's something we'll discuss here on the PowerPoint in just a second. So what I want to show you also is the cosine of x. Now, we could go through the same process by doing cosine of x, but let's kind of do it just by graphing cosine down here. Let's go cosine of x, and we'll change that color as well. We'll go to blue for no reason. Okay, and look at here. It looks exactly like sine of x, only shifted to the left a little bit, or to the right, depending on your whatever you want there. But notice we starting at 0, 1. We're at pi halves 0, pi negative 1, 3 pi halves 0, and 2 pi 1. So Notice it still goes up to 1 and down to -1, just like sine goes up to 1 and down to -1. Notice this entire curve right here, this little valley for cosine, repeats forever and ever. It goes here, it's down and up. Then it goes down and up. It repeats. Look how long that repeated section is. So on sine, notice the red dots that I chose go from 0 to 2 pi. Notice the dots that I did here for cosine are from 0 to 2 pi. That's a big deal because, again, we call that the period of the function. Okay, so that is the basics of the parent function. And a few things that I'll ask every once in a while is like, where does sine start? Sine normally starts right here at 0, 0, and then goes up to 1, down, and back to the middle. Where does cosine normally start? Cosine normally starts at the 1. It starts at the highest value, goes to a valley, and comes back up to the highest value. So let's go back here to this. Went backwards a little bit too far, accidentally. So the parent function, sine of x and cosine of x, we just did that on the table. But let's look at using A, B, C, and D. A represents what we call the amplitude of the function. Very easy. If A was 3, the amplitude is 3. But what does that mean? If you were to graph 3 sine of x, well, let's just look at that on, let's just go ahead and look at that on Desmos here. See what Desmos does. Let's clear these 3 equations. These 3 things. I don't need the table anymore. Let's clear that. We have sine of x. Let's see what 3 sine of x does. Amplitude means height. So notice what it does. Sine of x has a highest point of 1, where 3 sine of x has a highest point of, oh, look at there, 3. So it's how high the graph goes from the center. Okay, so in sine of x, it goes up 1 and it goes down 1. In 3 sine of x, it goes up 3 and it goes down 3. All right, pretty straightforward for amplitude. So how tall each wave is from center. The period of the function is determined by the b value, and it's how long the function takes to repeat one cycle. So that curve, that wavy curve for sine of x and cosine of x, this being sine of x, that one curve is 2 pi long. So if you're given a b value, in order to find the new period, if I said, hey, it's, let's not do cosine, let's do sine of 2x, the period is 2 pi over b. In this case, b is 2, and so it's pi, which means if we were to graph this, the graph would go from 0 to pi. One full wave curve here would go from 0 to pi. And again, we can verify this on this. If I said, hey, instead of 3 sine of x, let's go sine of x. But in this case, let's go 2x. Notice, the black curve here is the sine of x, and it goes from 0 to 2 pi here. And on the blue curve, one full wave goes from 0 to pi. It shrinks it shrinks horizontally. We can do the same thing. Let's say it's 1/2. Oops, that was not supposed to happen. Notice here, instead of going from 0 to 2 pi, it goes from 0 to 4 pi in the x direction. All right, so that is the period of the function. This takes a lot of practice, guys. That's why we're going to spend more than a week on this, on graphing. The phase shift. This, by the way, phase shift represents what we call it a phase shift, and we need to know this terminology. But this is called, in our normal terms, this is a horizontal shift. It's left or right. And it's C over B. And if this is a plus sign here, this plus C, then it moves to the left. And if it's a minus C, it moves to the right. Just like we did before. It's exactly like we did before with transforming graphs. So if I said sine of x minus 3, this is right 3. Whereas sine, and remember, anybody that said sine, it works the same for cosine. X plus 2, this would be left 2. And lastly, the D represents the vertical shift. It's kind of the easiest one. A and D are the easiest. And if it's a sine of x plus 3, it's up 3. And if it's a sine of x minus 4, it's a down 4. So it's how far should we shift up and down from the parent function. So a couple examples, non-graphing ones, but what I want to know is what's the amplitude and period. These are two all four of them are really very important, but these are two kind of the easy ones to figure out. I want to know what's the amplitude and period of these functions. So for amplitude, we just look for the number in front of the function. So we're going to say a equals 2. And some of you might as well just get in the habit of doing this for all the equations. A equals 2, B equals 1. And if we go a little bit farther, kind of more than this question is asking, we could say C equals 0 and D equals 0. So the amplitude is 2. And the period is 2 pi over B, which is 1, which is 2 pi. So in this case, the period is just 2 pi. How about the next one here? We have A is 0.5, B is also 0.5. It's the number in front of X. C is 0 and D is 0 again. And I think the couple that I have here, C and D are 0 for right now. So this A value is my amplitude, so it's only going to go up to 1/2 and down to -1/2. And my period is 2 pi over 0.5, but I don't want you to leave this. If I divide by 1/2, it's like multiplying by 2, so this becomes 4 pi. So for h of x, A is -4, B is 3, C is 3, and D is 5. Now, technically amplitude is not -4, but I'm fine if you guys say that. Amplitude is just 4. It tells you how far up and how far down. The negative just flips me over. Rather than for sine, normally sine would go up first. This sine is going to go down first and then up and over. Oops, what's going on here? Okay, the period for this function, 2 pi over b. So it's just 2 pi thirds, so I don't need the equal sign there. And obviously we have a phase shift and a vertical shift, but that's not important for the question that we're answering here. I have to eliminate some stuff here. So what is the phase shift then of this particular function? So phase shift, oops. I just abbreviate PS. Phase shift is given by C over B. In this case, C is the number here without the X, and a lot of times it's going to be a pi, or some version of pi, over B, which is 4. And then you need to determine direction. Because this is a minus, it goes pi fourths to the right. What that does is it changes our initial starting point. Rather than starting at 0, 0, it starts to the right at pi fourths 0. This one, again, easy, phase shift. C over B. I don't know why I wrote that again. C is pi. B is 2. The minus there tells me it's a shift of right pi halves. Okay, we're not going to try graphing on this particular video. What I want to do is I want to discuss how to graph. There are 2 methods for, right now, sine and cosine, obviously, how to graph. One method is my method that is more of a, I guess more of a trick than anything, but it's kind of how people that become familiar with graphing, they're able to graph in this manner. So what we do is use a pattern. And what this is using 5 points, using halves, using the starting point, and that stuff I'm going to get to here in just a second. So you need to find the starting point. Normally, sine starts at 0, 0. And cosine starts at 0, 1 from those graphs we did earlier on the Desmos. However, a phase shift of pi fourths to the right is going to change this to pi fourths, comma 0, and a phase shift of pi fourths there is going to be pi fourths 1 for cosine. So we just move things to the right or the left depending on the phase shift. We also use the vertical shift. If we had sine normally starting at 0, 0, but I said there's a phase shift of pi fourths to the right, and pi fourths, I guess, and 3 up, I'd change this 0 to a 3. Okay, so that's a starting point. We are going to find the last, or those of you that use this method, we're going to find the last point by using the period. So if I went to graph just sine of x, I know sine of x starts at 0, 0. I know one full period is 2 pi, and the last point has to be exactly where the first point starts. When I say know the middle, sine goes up, hits the middle, goes down, and in the middle. So I know the middle is at pi, and I know that has to cross at the middle. And then I know my quarters. I know halfway between the first 2 halves, I have to be up at the amplitude. And at the second quarter there, I have to be down. And then we just connect our graph with a smooth curve. I have seen people draw it this way, so maybe this would help. Rather than doing anything with pi, I would say this is, oops, I need the pen back. This is the period. This is the period over 2. This is the period over 4. And this is 3 times the period over 4. Okay, that might help a little bit rather than thinking about certain numbers. And it goes likewise for cosine. If I was to graph cosine, I say, hey, how do I graph cosine? Or some version of cosine. I know, first of all, I break it into 5 or 4 dashes out here. I know cosine normally starts at the up position. 1 full period away, it also ends up. Half the period away, it's all the way down at the amplitude. And then at the quarter and the 3/4 period, it crosses the x-axis, or the center line. Now there is another method. This method, the first method that I did, is kind of my method. It's probably other people do it as well, but it's a quick way to graph once you get the hang of it. But some people need this other 5-point method in order to actually do some calculations and finding points and graphing those points. So in our sinusoids, where we get sine of bx plus c, if you let this bx plus c equal these 5 numbers, oops, I missed a 5th number. If you let bx plus c, so you're basically doing this, bx plus c equals 0, bx plus c equals pi halves, bx plus c equals pi, and so on, and so on. Just for those 5. Once you get those x values from this, you can create a table. Those x values go there, and you just plug it in to find the y values, and that will work every single time, and you don't really have to think too hard. You just do these simple calculations, use your x values, and find y values. Now, notice I'm using pi halves. I'm not going to make this 1.57 because we use pi's on our graphs. So once you do the bx plus c equals to those 5 numbers, oops, I just eliminated that again. You substitute those x values into the function and solve for y, just as you would normally do for any graph. Now, if you want to write these down, these are the, 5 or 6? Oops. Where did my mouse go? All right, those are my 5 equations that we're going to graph in the second video. We're going to do them by hand. So we're going to I'll do some of them my method and some of them the full-on method, the 5 points. All right, this is, again, just a basic video, and the next video is going to be more in depth.